So, hi everyone, my name is Brian, and today I'm here to talk a little bit about HFSS, and more specifically, this is the first tutorial of a series that I intend to do, and today's tutorial is on developing a split ring resonator, which is a very nice structure, very common in metamaterials, and so the reason behind this is basically to help undergrad and maybe even grad students who are starting to use the software. And also part of the motivation is the lack of good tutorials on YouTube on this specifically. So I hope I can provide some quality at least. And for starters, I already apologize because my street is kind of noisy, so I hope the recording doesn't get bothered that much. So anyways, let's get into it. So basically this is Ansys Electronics, the student version 2024, so maybe you can get this. I don't know if you have to like sign in with an institutional email, but anyways, probably you can get this. And you have several tools here, and the one that we are going to focus on is HFSS. So you just hit here, it's going to start a design for you, and you notice that you have several windows here, so you can like control the size of it so that it fits you. So for me this is okay. So this is our design. I'm gonna save it already with the name, for example, SRR, Split Ring Resonator Tutorial, today's date. So this is okay. And okay, so first things first, the structure that we're going to build, we start off with something that's very common in a lot of radio frequency structures and microwave devices, which is basically creating a substrate, which is a dielectric material, and creating the ground plane. So this is the two first things that we're going to do. So you click here in order to create a 2D rectangle, so 2D figure. Then you just select any 2 points, and here you can, with a double click, change the name of it. So I'm gonna name it ground, and it's gonna have an orange color because I like to assign this to basically anything that's made of metal. Usually this in real life is copper, it's a copper sheet. Okay, so you can double click also here and define some sizes. So this is the position, the X, Y, and Z. And basically the first point, which is the origin of the image, basically is this one. So we're gonna use the X-axis for the width of our substrate, of our basically our sensor or resonator, and the Y-axis for length. So basically this is substrate width. Well, we are gonna centralize it, so it has to be over 2. Substrate length over 2, and in the Y position I'm gonna position it on substrate height. And why is that? Usually when you create anything, it's gonna have a default value of 0 on the Z axis. So basically I want everything that's important from our geometry, our split ring basically, on the Z equals 0 plane. So that's the reason why. It's just something that I usually do. And here I'm creating variables. So basically it prompts me to select what kind of variable is it. So it's a length value. I'm gonna choose, I don't know, maybe 30. Okay, substrate length, so it's length, and here I'm going to choose 50. This is totally random. I'm just assigning some dimensions. And here, it's maybe the only one that's not random. It is 1.6 because it's the usual height of the substrate of the FR4 sheet that we usually have on the labs. So, and here we define the sizes. So basically, substrate width and substrate length. Okay. And now you see that we're kind of lost here with our visualizer. So basically you click fit all, and orient is just so that if you rotate it in any funny way, it gets back to this kind of standard position, so, or orientation. So that's basically it. We have our ground plane. And now we're going to create a 3D structure, which is our substrate. So you choose the 2 points for the plane and then the height. This is going to be the substrate. And so we have two ways of changing its material. Basically, you can click edit here, or you can right click and then assign material. Okay, and you can choose, for example, the FR4 that they have here, which is this one, but just for the sake of the tutorial, I'm gonna create a new material. So add material, FR4 lab, and then we're gonna choose a slightly different relative permittivity, and the electric loss tangent, it's going to be 0.02. So that's all. Okay, and then we basically hit OK. Okay, so we're going to choose FR4 lab, and you see for 3D structures we can assign a material, but for example for this plane you cannot. So anytime you have a 2D structure or a plane figure, you basically want to assign a boundary to it. So in the case that we have a metal sheet, for example, copper sheet, we're gonna hit assign boundary and then perfect E, which stands for perfect electrical conductor. Okay. So okay, we have basics, and something else that's missing from the basics, it's our domain, basically, where our solver is gonna solve the fields, basically. So you hit here to create a box, and then you choose it kind of randomly. Okay, and this is gonna be our radiation box. You can choose air or vacuum, it doesn't matter that much. I'm gonna choose vacuum for now, and you can make it transparent just because it's not like a physical structure. Okay, and for this, okay, so we're gonna choose the same position, so minus substrate width over 2 minus substrate length over 2 and minus substrate height, and the same. So for the sizes, actually for the positions also, I'm gonna choose, actually I'm gonna multiply by a slightly bigger factor. So x size substrate 1.1, so a little bit bigger. 1.1 times substrate length, and also 1.1. Oh, actually on the Z size, I'm gonna choose, I don't know, radiation. I'm gonna define a new variable, radiation box height, and for now I'm going to choose 15 millimeters, just so that we don't lose any field. And here I'm going to do it like this. So, and minus 1.1 substrate height. You have to make it a little bigger, otherwise it kind of overlaps with your actual structure, and then when you validate your design, the software is going to complain about it. So that's all. And now you right click and then you define a boundary, assign a boundary, and you hit radiation. And now you can basically make it go away or be hidden here. And you notice that I created this substrate, but I didn't define the sizes correctly, so I can do this on this small window here, for example. So I can make it the same, minus substrate width over 2, minus substrate length over 2, and minus substrate height. You have to use these kind of variables, otherwise if you want to change anything in your structure or try to optimize it to get the best results possible, you cannot tweak these values and have it all correctly positioned. So it's kind of boring, it's kind of bugging at first to use so many variables, but once you get the hang of it, you notice how useful it is. So substrate length, width, and the Z size is also substrate height. Okay, now it's better. So now we're gonna actually draw over our substrate. So we can just hit here in order to have this kind of view and then fit all. Okay, so we're gonna start with our ring. So we just hit here in order to create a circle, and for example like this. And now we have to change its positions. So basically this is the ring, it's gonna be orange as well. And so on the x-axis I want it to be centered, so it's also it's 0. The default value for Z is also 0, which is good. We don't have to worry about it anymore. And on the Y position, so basically this is the center position, you're gonna have to trust in me a little bit for now, but it's gonna be trail length minus substrate length over 2 in order to be centralized. So this way the end of the trail where we're basically inputting and taking the output of our signal is going to be the end of it, or its edge is going to be centered or aligned with the center of the circle or the ring. So that's basically the reason why it's going to prompt me to choose. So length, and then I don't know, 25 for example, and the radius going to be 8. I don't know, ring radius, sorry, I just talked about this, and then 8. Okay. Right. So the trail length is kind of big. I chose it wrong. So if you want to change anything about, actually it's kind of small. So if you want to change anything about, or the values of the variables that you created, you just hit here, they're gonna appear, or you right click and then design properties, and they're here. And then I will choose, so for example, the length of the substrate is 25, so I'm gonna choose, I don't know, 35 here. Yeah, that's way better. And also, I think I'm gonna make it slightly bigger, like that. Okay. Right. So now I'm gonna create the actual trails. So just hit here in any way, and then I change it. Yeah. Okay. So this is trail, the original trail. And then, after creating the two trails here, I'm gonna finish the ring, just so you can see. Okay, so this is the original trail, and the position is basically, okay, so this is gonna be, also you're gonna have to believe in me a little bit, but after it's gonna make much more sense. So basically this is gonna be ring radius. I'm using the parentheses just to make it easier. So ring radius plus the trail gap plus the trail width, because you have a slight, very small gap in between the trail and the ring. This is on the y or the x, so the y is gonna be minus substrate length over 2, and the z we don't have to mind about it. I'm gonna make it 1 millimeter, I don't know. And the trail length, so the trail has gotta have an impedance so that it matches 50 ohms, which is usually the characteristic impedance that we use as reference in our circuits. Otherwise, you're going to have too many reflections before the electrical field can actually be coupled with the ring resonator. So at the frequency that you design it to operate. So for example, I'm going to design it to operate on 1.5 gigahertz, and that leads me to having a trail width of 3 millimeters. So for this, basically you want to use any kind, for example, you want to use any kind of microstrip line calculator like this, and then you can just prompt some parameters like the dielectric constant and the height and the frequency that you want, and then it's going to calculate these geometric aspects that you need, variables. So basically in my case it's 3 millimeters, I've calculated it, and here I'm gonna have, so trail width, and the y side is gonna be trail length. Okay, so that's it basically. And the first cool tool that I'm gonna show you is the mirror duplicate, which creates a copy and it's mirrored from the original. So basically you hit here and then anywhere here, and it's going to create this copy. So this is going to be trail mirrored. Okay. Afterwards we're going to connect them both. Now I'm going to actually create the ring, because you just have a circle here. So now we create another circle, concentric one, and then we don't have to name it, we just have to parameterize it. So x equals 0, right? The y position is the same as before, so trail length. That makes more sense, right? That's why I didn't go further with this. And the radius is going to be basically ring radius minus ring width. and then the ring width, I don't know, 2 millimeters, for example. So we're going to parameterize it like this. And why is that? It's because we're going to create the ring by subtracting this, or actually the smaller circle, from the bigger one. So you first click on the bigger ring, or the bigger center, or sorry, the bigger circle, and then you hit Control and click on the smaller one, and you hit on subtract. So now you have a ring, and it's got to be split, otherwise it's not a split ring resonator. This kind of small split, it's gonna basically, in terms of circuit elements, it's gonna represent a capacitance, while the metal itself represents an inductance. And for creating the split, you basically draw a rectangle here, so like this, for instance. And now I'm gonna call it split. So first of all, you notice that when I subtracted this, the smaller from the bigger, it kind of got into the bigger. It's gonna happen the same with the split, right? So basically this split, we're gonna position it here. So it's minus split with over 2 in order to be centralized. The position on the y-axis is the same. Trail length minus, basically this is the center. Trail length minus substrate length over 2. And then the x, okay, so length, and the split width, I don't know, 3 millimeters, for example. And then the x size is going to be split width. The y size is going to be the ring radius, so that it ends here. Okay, perfect. And now we're going to do the same. So hit first on ring, then control, then split, and then subtract. Okay, perfect. And now we're going to create the arc that connects these two. So the idea for this is that we're going to create a line here and then an arc in a 180 degree arc, and then we're going to basically integrate this line along the path that the arc forms. So for this, I think it's maybe better, okay, I'll leave it like this maybe, or just rotate it a little bit. So first things first, this is, sometimes it's kind of weird to rotate, but I think I'll make it. So I want it like this, right. It's obviously not perfectly aligned. It doesn't matter that much. So now we're going to create the line. So you just hit here, click on one edge, the other edge, and you click again on this edge, and then basically okay, so now I have this line, and wait here, okay, and then you define points. So the point 1 is going to be on the x-axis is going to be minus ring radius plus the trail gap, right, on the parentheses. And on the y-axis is going to be aligned, so trail length, the same story, trail length minus substrate length over 2. Okay, and now we can copy this, because it's probably going to be almost the same. We just add the trail width here, so plus trail width. Yes, perfect. So this is the line that we created, right? Okay. Yes, so we have the line here, and now we create the arc by selecting this one, draw center point arc. So it's basically this, and then this. So click, and then you click here again. So click on the center, click on the middle of this polyline, then click on the middle of this one, and you click again here, and then you end. You have this, so this is, I can change the name of it. I don't think I can. Okay, doesn't matter. Just so that we don't lose track, the second one is the arc that we have. So we have to parameterize it as well. So center point, for example, you can define it here. So this is 0 on the x, and the y is this one. I already copied it. Angle, it's minus 180, it's correct. And the start point, it's almost this. It's trail length minus substrate length over 2 on the y. And here, it's this gap plus the trail width over 2, because it's the middle of the trail, right? Okay. So it seems that everything is fine. Let me just double check. Yes, everything's okay. And now, if I'm not mistaken, I think you have to click on the polyline first, this one, and then control the second one, and then integrate or sweep along path. Okay, so you now have created this kind of arc, which you can, okay, for now, let me just change its color to orange, so that we know that it's metal. Okay, and I'm gonna name it trail arc or connection arc. Okay, perfect. So now we're just missing one thing, which, or actually two things, which is our ports, which are our ports. So now we can hit orient, and we need like an input port here and the output port here, for example. So for this, we're gonna first change the plane of reference, because we're gonna draw on the XZ plane. And then we hit rectangle. So for instance, you can click here to make it easier. Just hit on rectangle, hit, I don't know, here, and then here, any way you want. Then you can select it as input port. You make it orange if you'd like, and then you define it here. So on the x-axis is going to be okay, that whole story again. So let me just do it like this. So minus ring radius minus, or actually on the parentheses, ring radius plus trail gap plus trail width in this case. Then on the y-axis is going to be minus substrate length only, because we are not centralizing with the over 2, obviously. And on the z it's going to be minus substrate height. Right. And now for the x size we have trail width, and the z size is going to be substrate height. If I didn't do anything wrong, yes, it seems like it's good. Okay, and now we're gonna do that same thing with the mirror once again. So you select it, mirror duplicate, and then hit the center here in order to be the reference, and then you click here and you have the second one, which is the output port. Okay, good. And now we have to assign a lot of things. So for these two, which are ports, so you can click here, control here, and then you have to assign basically excitations for them, because you're gonna send a signal here and you're gonna also send a signal here, because you have S22 parameters, for example. If you don't know about S parameters, check out some lecture on it, because it's very important on this kind of context. And okay, so you're gonna assign an excitation here, port, and then modal lumped port. You can name it any way you want. And if you have 50 ohms, you just leave it like this. And then integration line, you hit new line, and then you click on the ground first here on the middle, and then on the top. So okay, and then you do the same with the second one. So assign excitation port, modal lumped port, okay, integration line, new line, and then like this. Okay, perfect. And now let me just orient it and then fit all. And now for the other stuff that we have, which is made of metal only, we just select them all with Control hold, and then assign boundary and perfect electrical conductor. Okay. And if you want to check your boundaries and your excitations, you can do it all here. So for example, if I click here, I can check this kind of excitation. Yes, so for instance, it looks like this. If I want to check this one, if it's selected, it's like this. So orient, fit to all, and then you can check also the boundaries. So for instance, perfect electrical E on the ground and on top, and then the radiation box also. Okay, that's very cool. So in terms of drawing, basically we've done it all. We have everything assigned. So basically you can hit here and then validation check. Okay, and this is my point. We haven't told the solver or the software how we're gonna analyze this. So which kind of frequencies we're gonna want to see or simulate. So now we have to hit here, analysis, and then add solution setup, advanced, and then here, for example, if you want to check frequencies all the way up to, I don't know, for instance 8 gigahertz, you choose something slightly bigger, so like 9 gigahertz for example. In this maximum number of passes, you can choose 10 for instance. So mesh solution options, here you can choose mixed order. This is the kind of solver you're using. Okay, what else? Direct solver. Okay, this is all fine. If you have a lot of issues, for example, with this kind of convergence, you can change this lambda target to something smaller, like 0.5 or less. But this is okay. Okay, I think that's basically it. Let me just check everything. Yes. Okay, this is fine. So you hit OK, and here, for example, I want to check from 1 gigahertz all the way to 8, for instance. So because of that, you have, in order for every point to be correctly positioned, basically you want to do like 8 minus 1, 7, so 700, and you add 1 point, so 701. Okay, linear count, points, yes. So everything is pretty fine. So you can just hit OK. And now it's got a setup, a sweep setup. So you can hit validation check. Okay, everything's fine, nothing overlaps. So I'm gonna clear this message so that we don't get confused. I just saved the project as well with Ctrl+S, and now we can simulate it. So basically you hit HFSS, analyze all, or you can also do it from here, analyze, which is safer. So here you can check the progress. So hopefully in a couple of minutes it's gonna be done with. So it's also very important for you to check whether your computer can handle this. That's why I'm using a remotely controlled desktop. Otherwise it would probably be impossible with my own computer. So you need a lot of RAM and some good processor or graphic unit. So that's basically it. Let's wait and see. Okay, so it took actually like 3 minutes in order to complete it, so it's pretty fast. And now we can plot something to see the results in general in this kind of broadband analysis. So you can right click here on the results and then create modal solution, rectangular plot, and then for instance as parameter, and you can hit Ctrl and choose more than one. I'm gonna choose the reflection 1.1 and transmission 2.1 in dBs. Okay, so here basically you can see how it behaves, and you can also, for instance, change its geometry, analyze the sweep all again, and then try to see it once again. So for instance, it has kind of like a not really good behavior. You can, for example, add a marker here in order to be able to, for example, see this slight point. So it's in 2 gigahertz. Here I have it in 1.4. So it's not very close to what I expected. I'm gonna tweak a little bit the geometries, the dimensions, and show you how it changes the solutions. So I'm gonna be right back. Okay, so I just finished sweeping it once again, and now I'm gonna create another rectangular plot. As parameter, S1, new report. Okay, got one over the other, which is not ideal, but in any case, you can notice how it seems like it shifted a little bit to the left, and I made the dimensions smaller, you see? So you can notice here and here. You can copy these dimensions, take a photo, for example, if you want, or a print. So I made it smaller, and now it looks like this. Sorry, looks like this. Yes. So, for instance, you can notice how it kind of shifted when you made, for example, I made the ring radius bigger, the split width smaller, the substrate dimension smaller, and it seems like the quality factor got a little bit better because now you have less transmission on a closer frequency. So for instance, you can check this marker here and notice that it's in 1.52 gigahertz, which is pretty cool. So I like this result, and now I want to show you guys how you can plot the fields in order to see this kind of behavior. So basically what you want to do is you hit here, and now you're going to create a plane. So when you click here, it's going to say a solution exists, and you say yes. You change the plane of reference, of course, and then you choose this edge, basically. This is the fields plane, I don't know, fields plane, and it's good to make sure that this is in the right position as well, so minus substrate, in order to be rigorous, okay? Substrate width, substrate length, over 2, yes, and then substrate width, and substrate. Fine. You can also notice that the values here didn't change because it was already right, but if you parameterize it like this, it's better. And now, for example, you can choose this geometry, and then you can sweep here and then go field overlays, plot fields, E, complex mag E, for instance. Okay, so of course, something that you have to do previously is to create a single frequency sweep. So it's you have to create a new setup or a new sweep. Let me go here, frequency sweep, and then you're going to choose discrete and then single point, and you define it, for example, at our interest frequency, which is 1.52. say fields, check. Okay, and the sweep name is going to be single sweep, single frac sweep. Okay, so now we have the right sweep, and you can plot the fields. So plot fields, E, complex mag E, and then you create this setup, for instance, of course, done. And something that you will notice, for example, is that we have this kind of issue. So what happened is that we defined the sweep, but we didn't solve it. So let's analyze this. So I'm showing you common issues, common errors that a lot of mistakes that people do. But now the cool part is that it shows it already. So in this case, it's kind of saturated. You see that there's no field here. So let me do it like this. Yes. So there's no field here, but this is just because of the scale. So if you click on modify, right click here, modify, scale, and then instead of auto you choose the limits, and you choose, I don't know, like 30,000 for instance. Apply. It's a little better, not that saturated. Let's use 20,000. Oh, sorry. Wait, this is right. Okay. Yes. So you can notice that basically all the field is coupled here, but you have some on the input, but you have none on the output port, because the transmission here is very small. As we notice, it's less than minus 10 dB, if I'm not mistaken. Let's check. So right, so it's minus 12 dB. minus 13 basically. So yeah, you don't have that much, and you can plot the fields here. So this is all of first lecture, first tutorial. I hope I could help you somehow. I hope you enjoyed. If you have any suggestions, just hit on the comments, let me know, and I'll try and do it. Okay, so thanks for watching, and see you next time.